In this video, we want to learn how we can use double-angle identities to prove other identities. Here we have a list of double-angle identities. Sine of 2 theta is 2 sine theta cosine theta. Cosine of 2 theta is cosine to the 2 minus sine to the 2, or 1 minus 2 sine to the 2 and 2 cosine to the 2 minus 1. And finally, tangent of 2 theta is 2 tangent theta all over 1 minus tangent to the 2 theta. These are the double angle identities that we need through this video. For proving identities, usually we start from one side of the equation, which usually that side is the part that is more complicated. For example, to prove this identity, we start from the left side, because as you can see, in the left side, we have a more complicated expression than the other side. So we start from, in this case, left side, and we try by using appropriate identities and algebraic manipulations, arriving to the other side. The selection of appropriate identities to obtain the desired result is learned only through experience and, of course, lots of practice. In the left side, we have 1 minus cosine 2x over sine of 2x. By looking at the other side, we can see that in the right side, we have tangent x. But as you can see in the left side, we have double angles for cosine and sine. So it can be a good idea to use these double angle identities to change these angles to x. Because by using these identities, we can change the angle 2 theta to theta. So here we have 2x, and in the other side, in the right side, we have x as the angle of the trigonometric function. So this is the reason that we can think to using these double angle identities here. For cosine 2x, if you pay attention, which is in the numerator, as you can see, we have three formulas: cosine to the 2 minus sine to the 2, 1 minus 2 sine to the 2, and 2 cosine to the 2 minus 1. Which one of these is better to be used here? For choosing between these three formulas for cosine of 2 theta, you have to attention to the other terms that you have in your expression. For example, here, as you can see in numerator, we have a 1 here, then minus of cosine of 2x. So 1 minus. Now you have to think which one of these expressions it's good to we substitute for cosine of 2x such that it can help us to simplify the numerator better. If you pay attention, if we use the middle one, if we use 1 minus 2 sine to the 2 for cosine, so if we suppose we use this one here, why this is a good idea? Because then we have 1 minus 1, and this one with 1 cancels. But suppose you use, for example, the last one. Suppose you use 2 cosine to the 2 minus 1. Then what happens? You have 1 minus negative 1, which is 2. 1 plus 1 then you have, and you have 2 minus 2 cosine to the 2. So nothing simplifies. So probably better idea here is to use the middle one. And why not the first one? Why this one is not a good idea to use? Because then you have 1 minus cosine to the 2 x minus sine to the 2 x, because here is 2x, so it should be x here. Then, as you can see in the numerator, you have 1 minus cosine to the 2 plus sine to the 2. So, to decide between these three formulas that we have for cosine, you have to look at the other terms that you have in the numerator and sometimes in the denominator. Then, by considering the other terms, you can choose the proper one. But attention, if you make a mistake and you choose not the appropriate substitution, then still you can continue working, but getting to the desired result would be a little harder. I will show you, for example, how we can use, for example, this one to simplify this expression and get to the other side as well. So I show you two methods basically. But of course, if you use the better one, you can get the desired result faster. So let's continue. Here, for simplifying this expression, for cosine of 2x in numerator, we substitute cosine of 2x with this rule. 1 minus 2 sine to the 2x. Because it is cosine of 2x, so we have 1 minus 2 sine to the 2x. And for the denominator, sine of 2 theta is 2 sine theta cosine theta. So sine of 2x is 2 sine x cosine x. If we simplify, for denominator we can do basically nothing. We write the denominator again. But for numerator, 1 minus 1 cancels. So in numerator we have only 2 sine to the 2x. 2 sine to the 2x. Because don't forget you have a minus here, times minus would be positive. Minus times minus, negative times negative is positive. So we have 2 sine to the 2x in numerator. Now simplify numerator with denominator. 2 with 2 cancels. Sine to the 2 is sine x times sine x. 1 sine x from numerator. Sine to the 2 is sine x times sine x. 1 sine x with 1 sine x cancels. What remains? Sine x over cosine x. So the answer is sine x over cosine x. But we know that sine over cosine is tangent x based on the quotient identities. Sine over cosine is tangent. Sine x over cosine x is tangent x. So we proved this identity. And for cosine, we use this middle identity that we have. Now let me show you how we can use the other identities for cosine to get to the other side. But of course, it will be a little harder to get to the other side. But still it works. So, for example, let's say we use this for cosine. 1 minus cosine to the 2 x minus sine to the 2 x all over sine of 2x. But of course, for sine of 2x, we substitute with 2 sine x cosine x. Now we want to simplify this and get to the other side. If we simplify numerator, we have 1 minus cosine to the 2 plus sine to the 2x. 1 minus cosine to the 2 minus times minus would be plus. Now look at the numerator. 1 minus cosine to the 2, which we have in the numerator, 1 minus cosine to the 2 is sine to the 2 based on the Pythagorean identity. If you remember, always we have this important rule. Sine to the 2 plus cosine to the 2 is always 1. So based on this identity, 1 minus cosine to the 2 is sine to the 2. So 1 minus cosine to the 2x is sine to the 2x. Now by using this, we have sine to the 2x plus sine to the 2x over 2 sine x cosine x. So in numerator we have 2 sine to the 2x all over 2 sine x cosine x. Now simplify the numerator with denominator. 2 with 2 cancels. 1 sine from numerator with 1 sine from denominator cancels. So this goes with 1 power here. So it becomes 1 here. Now we have sine x over cosine x, and sine over cosine is tangent x. So as you can see, with using the other formula for cosine, also we can get the desired result. We can get to the other side. But of course, if you use the better substitution, you can get to the other side easier and faster. Now let me show you another examples. We want to prove that sine theta plus cosine theta all to the power of 2 is 1 plus sine of 2 theta. Usually for simplifying, for proving identities, we start from the part that is more complicated and we get to the other side. But sometimes happens that we have to simplify both sides. We simplify the left side, we simplify the right side, we get to the same expression after simplification of both sides. And because we get to the same expression, by doing this, we can show that both of them are the same. But usually we try to simplify only one side. And that side is the side that is more complicated. Here, which side is more complicated? What do you think? The left side or the right side? For me, it seems the left side because we have a bracket, two terms in the bracket raised to the 2. But in the right side, we have just a number 1 plus sine of 2 theta. So I prefer to start from the left side, simplify it, and get to the other side. And basically, this example is a very famous example for proving identities. Sine theta plus cosine theta all to the 2 is 1 plus sine 2 theta. So for proving this, the first thing that we can do is to raise this bracket, of course, to the power of 2. Because for the inside, we can do nothing. Sine theta plus cosine theta. We don't have any formula, any identity for simplifying the inside of the bracket. Because we don't have any basic identity or double angle identity. Nothing basically. We can think to raising the bracket to the power of 2. For raising the bracket to the power of 2, either you can use this identity, a plus b to the 2 is a2, 2ab, b2. I highly recommend you to memorize this identity. A plus b to the 2 is a2, 2ab, b2. If you don't like to memorize it, then you have to multiply this bracket by itself twice. But by using this identity, you can get the answer faster, of course. But here we suppose that we don't know the identity and we start multiplying sine plus cosine by itself. So we have sine theta plus cosine theta, this is the left side, times by sine theta plus cosine theta. By multiplying these brackets with the FOIL method, first term in the first term, sine times sine is sine to the 2. Then the outer terms, sine times cosine, we have sine theta, cosine theta. Then we have cosine times sine is the same as sine times cosine, is the same as this term. So we have 2 of these terms, so this becomes 2, sine theta, cosine theta, and finally cosine times by cosine is cosine to the 2. So again, please pay attention, sine times cosine is the same as cosine times sine. That's the reason that we have 2 of this. Now we have to simplify this expression. Sine to the 2 plus cosine to the 2. When we look at these two, immediately we remember the Pythagorean identity. Sine to the 2 plus cosine to the 2 is always 1. What about this? This should remind you sine of 2 theta. Look at here. Sine of 2 theta is 2 sine theta cosine theta. Sometimes we use this identity in the opposite order. We have this, we substitute this with this formula. 2 sine theta cosine theta is sine of 2 theta. Now look at the next identity that we want to prove. Tangent theta plus cotangent theta is 2 over sine of 2 theta. Again here, the more complicated side is the left side. So we start from the left side. Tangent. Usually we write tangent in the form of sine of cosine by the quotient identities. And cotangent is cosine over sine. Now we have 2 fractions. What do you do when you have 2 fractions? Common denominator. Let's say I am asking you what is 2/3 plus 1/5. What do you do here? Common denominator. By doing common denominator, you can combine the 2 fractions to a single fraction. And look at the right side, you have a single fraction. So Of course you have to do this. So we do a common denominator. The common denominator between cosine theta and sine theta is sine theta times cosine theta. The common denominator in this case is simply multiply the denominators by each other. So a common denominator is cosine theta times by sine of theta. For the numerator, what we have? In this fraction, we had cosine only in the denominator. Now the denominator, the common denominator is cosine times sine. So the denominator, this denominator is multiplied by sine. So when you multiply the denominator by anything, you have to multiply the numerator by that thing. So you have to multiply this sine by another sine. So in numerator you have sine to the 2. For the other fraction, here we have a sine theta. But the common denominator is cosine theta sine theta. So the denominator is multiplied by cosine. So multiply the numerator of this fraction also by a cosine. And then the numerator would be cosine to the 2. So plus cosine to the 2. Look at the numerator. What do you notice immediately? Right away. Sine to the 2 plus cosine to the 2. Again. Sine to the 2 plus cosine to the 2 is 1. So we have 1 over sine theta cosine theta. Now, attention that we want to get from this side to the other side, to this. It seems that we are almost done, but what we have to do to get from this to that? Here in denominator we have sine theta cosine theta, but here in denominator is sine of 2 theta. Let me remind you the double angle identity that we have for sine of 2 theta. Sine of 2 theta is 2 sine theta cosine theta. So, whenever we have this expression 2 sine theta cosine theta, we can substitute this with sine of 2 theta. But here we only have sine theta cosine theta without these 2. If we had these 2 here, you have to remember this. If we had these 2 here, then 2 sine theta cosine theta is sine of 2 theta. But we are not lucky here. We don't have that 2. Again, if we have a 2 here, then all of this is sine of 2 theta. But what we can do here, we don't have that 2 here. It's easy. You want to have that 2 in the denominator. You know that. When you have a fraction, you can multiply the numerator and denominator by anything that you like, by any expression, any term. But you have to do with the numerator and denominator. So you have to multiply whatever you multiply with denominator, you have to multiply by the numerator. Because here we need a 2, so we multiply the numerator and denominator of this fraction. We multiply the numerator and denominator by a 2. So we have 2 over 2 sine theta cosine theta. By multiplying a 2 with numerator and denominator, we have 2 over 2 sine theta cosine theta. Now, by looking at the denominator, we are happy because we have an identity for that. 2 sine theta cosine theta is sine of 2 theta. So this equals 2 over sine of 2 theta. 2 over sine of 2 theta. Now we get to the other side. Before I show you more examples in this video for double angle identities, how to use them to get the desired result, let's talk about this identity and in general identities, how we have to learn them, we have to, if we want, memorize them in the proper way. Only by memorizing 2 sine theta cosine theta is sine of 2 theta. You cannot really use the identity. You have to understand relation between the two sides of the identity. Please pay attention. Sine of any angle. This is the way that I memorize the identity. I'm not saying sine of 2 theta. Sine of any angle. You have to keep it in this way in your head. Sine of any angle is 2 sine of half of this angle. Whatever the angle is in the left side, in the right side is half of this. So sine of 2 theta is 2 sine of theta. So to memorize, to learn, to understand an identity, you have to pay attention to the details. Here, whatever is here is half of that, and also here. So sine of 2 theta is 2 sine of half of this angle, cosine of half of that angle. By learning this way, if I ask you, what is sine of 10 theta based on this identity, then you are able to say this equals 2 sine of 5x cosine of 5x, because you know that the relation between this angle and the angles that we put here and here is that whatever is here is half. We have to divide it basically by 2 and put it here. 10 theta, 5. 10x, suppose this is x, this should not be theta. Sine of 10x is 2 sine of 5x cosine of 5x. So this should be x, not theta. Sine of 10x is 2 sine of 5x cosine of 5x. Let me ask you another one. Suppose I am asking you simplify sine of 20 and write it in the terms of sine of 10 and cosine of 10. Then based on this identity, this equals 2 sine of 10 cosine of 10. Maybe you wonder why we need this when we use this identity in this way. Suppose, for example, you want to simplify this expression, sine of 20 over sine of 10. Immediately you can write sine of 20 as 2 sine of 10 cosine of 10 all over sine of 10. Then this sine 10 with sine of 10 cancels, and the answer is 2 cosine of 10 degrees. So, learning an identity is different than memorizing an identity. And attention, not only you have to learn how to use this identity from left to right, you have to understand how to use it from right to left. 2 sine of cosine of an angle is sine of double of that angle. For example, let's say I'm asking you simplify this. 2 sine of 15 cosine of 15. This equals sine of 30 degrees. What happened here? 2 sine of theta cosine of theta is sine of double of the theta. Double of whatever is here goes here. And sine of 30 degrees, as you know, is 1/2. So, for all the identities, not only double angle identities, for all the identities in math, you have to learn them in this way that I explained to you. You have to practice with them. You have to attention to the details of the two sides of the identity. And gradually, you can learn this technique, these things better and better. And the best way for learning identities, one of the best way definitely, is doing lots of practice with that identity. Okay, let's move to the next examples. Cotangent x minus tangent x is 2 cotangent of 2x. So, for this one, cotangent can be written as cosine over sine. So, cosine x over sine x by the quotient identities, and tangent is sine x over cosine x. We do a common denominator here again, similar to the previous question. The common denominator between sine x and cosine x is sine x times by cosine x. What would be the numerator? The numerator simply would be cosine to the 2. This is very similar to the previous example that we did. This is the numerator, cosine to the 2 minus sine to the 2. Basically, we multiply this by this, we multiply this by this. Now look at the numerator, look at the denominator. Cosine to the 2 minus sine to the 2. This should remind you, if it was plus here, then it's 1. Sine of to the 2 plus cosine to the 2 is 1, based on the Pythagorean identity. But here is minus. Cosine to the 2 minus sine to the 2 should remind you the cosine of 2x, this identity. The double angle identity for cosine. Remember? Cosine of 2 theta is cosine to the 2 minus sine to the 2. Now we have this side, so we can write it as cosine of 2 theta. But you have to have a good reason to write this in this form. Not because we have this identity, definitely we have to use this identity. No. The other reason that it's a good idea to use that identity here is that in the right side, that we want to get to that side, we have cotangent of 2x. So it's a good idea to have cosine of 2x. Double angle identity. What about the denominator? Sine x, cosine x. If you remember from the previous example that I showed you, again, we remember that if we have 2 sine x cosine x, this is sine of 2x. But we have only sine x cosine x. What we can do here? Simply we can multiply the denominator by a 2. So then we have 2 sine x cosine x. And of course we have to multiply the numerator by that 2. So here, one way is to do this. Multiply the numerator and denominator by a 2. Then you have 2 sine x cosine x. And you can substitute all of the denominator, all of this, with sine of 2x. The other way for this is, let me show you. What is the other way? We know that sine of 2x is 2 sine of x cosine x. But we don't have these 2 here. Because we don't have these 2 here, you can think it this way. How we can get rid of these 2 here also? By dividing right side and the left side by the 2. So these 2 with these 2 cancel. Then sine x cosine x is sine of 2x divided by 2. Then you can substitute this expression sine x cosine x, forget these 2 here. Sine x cosine x with sine of 2x over 2. So this is the other way. Let me show you both of these techniques here for simplifying this expression. Once, let's suppose we multiply the numerator and denominator by a 2. So a 2 here, a 2 here. So for numerator we have 2 here. And for denominator, now we can substitute all of this with sine of 2x. And this equals 2 cosine of 2x over sine of 2x. We know that cosine over sine, focus on this, cosine over sine is cotangent. Cotangent is cosine over sine. When it is cosine of 2x over sine of 2x, it is cotangent of 2x. So this equals 2 cotangent of 2x. We get to the other side. Now let me show you the other method for simplifying this expression here. How we can get to the other side without multiplying the numerator and denominator by 2. In this method, let me remember you again. Sine of 2x is 2 sine of x cosine x. When we don't have these 2 here and only we have sine x cosine x, sine x times cosine x is basically 1/2 sine of 2x. Why? Because we have a 2 here. By dividing both sides by 2, this 2 is gone from here and we have a 1/2 here. Or sine of 2x divided by 2. It's the same as 1/2 sine of 2x. So, now we continue this way. The numerator is cosine of 2x. We know this. The denominator, this expression, is sine x cosine x, which is 1/2 sine of 2x. 1/2 sine of 2x. Now you know that when we have a fraction, and in the denominator of fraction we have a 1/2 fraction, this fraction we can bring it to the numerator, but we have to flip this. If we flip 1/2, it would be this 2 here. And cosine over sine is cotangent. Let me explain this in more detail to you. So far we know that sine x cosine x is 1/2 sine of 2x. Or, if you like, you can consider this as sine of 2x divided by 2. It's the same. Sine of 2x over 2. For dividing expressions, when you have a compound fraction, this is the same as cosine of 2x divided by sine of 2x over 2. You know that when we want to divide two fractions, we change division to multiplication, but we invert the second fraction. If we invert sine of 2x over 2, or reciprocal of sine of 2x over 2 is 2 over sine of 2x. And this equals 2, we have these two, cosine over sine. Cosine is in numerator, sine is in denominator, and it is cotangent of 2x. 2 cotangent of 2x. Maybe you think by yourself, why we have to learn different techniques? Because when you have different techniques, you know different techniques, you can use the proper one depending to the situation. If you know only one technique for simplifying expressions, then maybe that technique doesn't work really well in that situation, in one particular question. Learn different ways for simplifying, then you can get better and better, and because you have more skills, you can simplify easier. So finally, we prove that this equals 2 cotangent of 2x. We prove this in two different ways. Look at the next one, cosine to the 4 minus sine to the 4. Let me remind you a very important, very famous identity. A to the 2 minus b to the 2 is a minus b, a plus b. But maybe you wonder why I have to remember this. What is the relation between this identity that you are writing here and this question? I can see no relation. Whenever we have two terms and a minus between them, you have to immediately remember this identity. Then you can say that you know this identity. If you don't remember this identity, when you have this expression, then it means that you don't really know this identity. You have memorized this, but it's different than learning this identity. Whenever we have two terms with a minus between them, and this is important, these terms are perfect squares, a to the 2, b to the 2, cosine to the 4, sine to the 4. Then you have to remember this identity. A to the 2 minus b to the 2 is a minus b times a plus b. But maybe you wonder why I have to remember this. What is the relation? Because if you pay attention, by using this identity, you can write the left side in the form of cosine to the 2 minus sine to the 2 times cosine to the 2 plus sine to the 2. What happens in this identity? A to the 2 minus b to the 2 is a minus b. What is a minus b? A minus b is basically a square root of a to the 2 by considering a positive expression, which is a. A square root of b to the 2 is b. So basically you divide the powers by 2. If we divide this power by 2, 2 becomes 1 and 1 here. Now here the power is 4. If we take a square root, or if we divide the power by 2, cosine to the 4 would be cosine to the 2 minus sine to the 2, cosine to the 2 plus sine to the 2. So we use this identity. So we write this expression cosine to the 4 minus sine to the 4 in the form of cosine to the 2 minus sine to the 2 cosine to the 2 plus sine to the 2. Whenever the powers is even, we remember the identity. Here also the power is even, cosine to the 4 sine to the 4. Now look at the brackets. Immediately you should say this is 1. What is this? Cosine of 2 alpha. So this equals cosine of 2 alpha, which is the right side. So we proved this identity. At first it seems simple, but you have to be good at algebra identities. Otherwise, if you don't remember the identity, the proper identity, then it's really not easy to prove this relation here. Look at these examples. 2 tangent x over 1 plus tangent to the 2x is sine of 2x. 1 minus tangent to the 2 over 1 plus tangent to the 2 is cosine of 2x. As we can see, these two identities that we want to prove are really similar. One of them is for sine, the other is for cosine. Later, if you take calculus course, you will see that we have a substitution in the calculus course, which is famous to Weierstrass substitution. Weierstrass was a mathematician. And these rules, these identities, are useful for the Weierstrass substitution. But that's another story. Focus on this. We want to prove that 2 tangent x over 1 plus tangent to the 2x is sine of 2x. Which side of this relation is more complicated? Of course, the left side. So we start from the left side, we simplify that, and we want to get to the other side. 2 tangent x would be 2 sine x over cosine x. 2 tangent is sine over cosine. 2 tangent x is 2 sine x over cosine x. What about this? For this, you have two choices. You can say 1 plus tangent to the 2 is 1 plus sine to the 2 over cosine to the 2. Then if you do a common denominator between these two, you would see that this equals 1 over cosine to the 2. And finally, by simplifying this, 1 over cosine is secant, so this is secant to the 2. But instead of writing all of this, there is a better way for simplifying this denominator. If you remember the Pythagorean identities, one of the Pythagorean identities was 1 plus tangent to the 2. 1 plus tangent to the 2 was 1 plus tangent to the 2 is secant to the 2. So immediately we write, instead of 1 plus tangent to the 2, secant to the 2. So all of the denominator is secant to the 2. But again, if you forget this, it's not really important. Just simply replace the tangent with sine over cosine. Tangent to the 2 is sine to the 2 cosine to the 2. Again, you can get the answer, but it takes a little more time. You need more operations to do to get to the other side. Let's continue with this. We have in numerator 2 sine x over cosine x, and attention, this is our main fraction. The fraction that we have is here. This is the numerator of the fraction, and this is the denominator. While looking at the numerator, we can see that we have sine and cosine, but in denominator we have secant to the 2. We don't like to work with secant, and especially in the right side, if you look for, we have sine, we don't have secant. So let's use a technique to get rid of secant. What identity we have to use for here? Secant is 1 over cosine based on reciprocal identities. So we can write this as 2 sine x over cosine x all over 1 over cosine to the 2. Secant to the 2 is 1 over cosine to the 2. Now we have a fraction divided by another fraction. Usually the students here simplify this in this way: 2 sine x over cosine x divided by 1 over cosine to the 2. Then they change division to multiplication, and they flip this, which they bring this to numerator, they move this to the denominator. But this is really a slow method. When you have a fraction over another fraction, the fastest way for dividing a over b by c over d is ad over bc. Multiply far by far, multiply close by close. The d is far from a, so multiply ad, a by d, and multiply b by c, bc. So the answer is ad over bc. And attention, if this denominator is the same as this denominator, you can simplify them. If numerator is the same as numerator, you can cancel them if they are the same. If they have a common factor, you can cancel numerator with numerator, denominator by denominator. So here, in this question, if we use this technique, what happens? We can simplify this a little faster. This goes in top and this goes in the bottom. So we have 2 sine x cosine to the 2 all over cosine x. Maybe you are asking yourself, can we simplify this with this? Yes, you can cancel one cosine from this denominator with one cosine from this denominator, because the terms that are in the denominator, you can simplify them with each other. As you can see also here, they cancel each other. Cosine x with one cosine cancels. But you can do this here before multiplying this by this, far by far, close by close, before this, which would be a good decision to simplify one cosine from here with one cosine from here, because if you cancel one cosine from here with one cosine here from here, then you have only a cosine x here. Then cosine x times 2 sine x would be 2 sine x cosine x. So you can get to the answer faster. But I'm supposing we don't find this and we forget to simplify. So let's continue from here. 2 sine x cosine to the 2 over cosine. The cosine from numerator, one cosine from numerator with one cosine from denominator cancels, and then we have 2 sine x cosine x. And if you remember, 2 sine x cosine x is exactly sine of 2x, the other side. So we proved this identity, this important basically identity. Now look at the next example. 1 minus tangent to the 2 over 1 plus tangent to the 2. The process should be very similar. 1 minus tangent to the 2, we don't have any relation for that. So, for tangent to the 2, simply we write 1 minus sine to the 2x over cosine to the 2x. What about the denominator? 1 plus tangent to the 2. For 1 plus tangent to the 2, from here we know that we can replace it with this, and finally we have to replace that with 1 over cosine to the 2. That's one way. The other way is to simply write the denominator as 1 plus sine to the 2 over cosine to the 2. Then by doing a common denominator between these two and simplifying that, you would see that at the end you get this. So as you can see, there is no unique way to simplify expressions. It depends which identity you are using. But at the end, if you do the operations in the right way, you can get to the other side. Maybe a little later, but you can get to the other side finally. So here I'm going to use this way. Of course, the faster way is to replace all of this with only 1 over cosine to the 2. But let's do it this way, the longer way, not the best way. Okay, how we have to simplify this expression? It seems really complicated. 1 minus sine to the 2 over cosine to the 2 all over 1 plus sine to the 2 over cosine to the 2. Here, maybe you are thinking to doing a common denominator between these two, common denominator between these two, then divide numerator by denominator. It's a very good idea. But let me show you a better way to simplify this compound fraction. To simplify this fraction here, 1 minus sine to the 2 over cosine to the 2 all over 1 plus cosine to the 2 over cosine to the 2, instead of doing common denominators between numerator, the terms in numerator, and between these terms, the better way is to try to get rid of denominators instead of doing common denominator. How we can get rid of this and this? What are the denominators? Denominator is cosine to the 2. To get rid of cosine to the 2, simply you can multiply all of the numerator and all of the denominator by cosine to the 2. The reason that we multiply the numerator and denominator by this is that in denominator we have cosine to the 2. And if we do common denominator, the common denominator is also cosine to the 2. But the better idea is to get rid of, eliminate the denominator. And for that, we multiply the numerator and denominator by cosine to the 2. Let's see what happens by this. Then we have cosine to the 2 times 1 is cosine to the 2. Minus cosine to the 2 times by this, the cosine to the 2 from denominator with cosine to the 2 from numerator cancels, and we have this sine to the 2. This is for numerator. Now look at this expression and compare this with this original one. This is much better expression, and it is better than common denominator. For the denominator, if we multiply cosine to the 2 in the bracket, we have cosine to the 2x plus sine to the 2x. Cosine to the 2 plus sine to the 2 in the denominator is 1, so all of the denominator is 1. What we have in numerator, cosine to the 2 minus sine to the 2. If you remember, this is exactly cosine of 2x. And cosine of 2x over 1 is cosine of 2x. We got to the other side. So this completes the proof of this identity. Look at this example. Cosine over plus sine theta over cosine theta minus cosine theta minus sine theta all over cosine theta plus sine theta is equal to 2 tangent of 2 theta. It is clear that the left side is more complicated, so we start from the left side, we try to simplify that and get to the other side. In the left side the angles are theta, in the right side the angles are 2 theta. So it is clear that we need double angle identities at some point during simplification of the left side. In the left side we have two fractions subtracted from each other. What you have to do? Common denominator. So what is common denominator between cosine minus sine and cosine plus sine? Again, let me remind you, a minus b times a plus b is a to the 2 minus b to the 2. What is common denominator in the left side? The common denominator is cosine theta minus sine theta times by cosine theta plus sine theta. This is the common denominator. By this common denominator, we had this denominator here. Now we have multiplied the denominator by this, so we have to multiply the numerator, which is this, by this as well. And cosine theta plus sine times cosine plus sine would be cosine plus sine to the power of 2. But I prefer to write it in the form of cosine plus sine times by cosine plus sine, because maybe we don't know the rule for a plus b to the 2, and so we prefer to multiply the brackets by each other, not raising the bracket to the power of 2. So I prefer to write it this way. Of course, the other way is a little better because it's faster and you can find the answer easier. But let's continue with this form. And we have, for the other numerator, we have this, and we have to multiply it by this, so we have cosine minus sine times cosine minus sine. Now we have to multiply the brackets in numerator. To simplify this, we have cosine times cosine. We multiply term by term with the FOIL method. Cosine times cosine is cosine to the 2. And we have cosine times by sine. Then we have sine times cosine, which is the same as cosine times sine. So we have 2 of these terms. So we have 2 cosine theta sine theta. And finally we have sine theta times sine theta, which is sine to the 2 theta. Minus, this is the tricky part of the story. When you multiply this bracket by this bracket, don't forget you have a negative here. So multiply every term by every term, but apply this negative for every single multiplication that you do. If you forget this, everything would be wrong. So cosine times cosine is cosine to the 2, but if you have a negative, so minus cosine to the 2. Then we have cosine times negative sine, but we have a negative here, so plus cosine times sine. So we have cosine theta sine theta. Then we have this negative sine times by cosine. It would be negative sine cosine with a negative plus sine cosine. But we have another sine cosine already here, so it would be 2 cosine sine. 2 cosine theta sine theta. And finally, we have cosine times, not cosine. Finally, we have this minus sine theta times minus sine theta would be sine to the 2. With a negative here, minus sine to the 2. This is for numerator. What about the denominator? Is it a good idea to multiply these brackets by each other? In this case, yes it is, because when we multiply cosine minus sine by cosine plus sine, based on the identity a minus b times a plus b, it would be cosine to the 2 minus sine to the 2. First of all, it simplifies. We get only 2 terms, cosine to the 2 minus sine to the 2. A minus b times a plus b is a to the 2 minus b to the 2. So we multiply the denominator, because usually we prefer to leave the denominator in the factored form. But here, because it simplifies, if we multiply the brackets in the denominator, so we multiply them. But the other reason is that now this is familiar to us. Cosine of 2 theta. Cosine to the 2 minus sine to the 2 is cosine of 2 theta. And if you look at the other side, it's 2 theta as well. So we have several reasons to multiply the brackets in the denominator. For numerator, yes, usually we multiply the brackets, but for denominator, usually we prefer to keep it in the factored form. But this case, because it simplifies and we have a formula for that, it's a good idea to simplify and multiply the brackets. Now look at the numerator. Cosine to the 2 with cosine to the 2 cancels. Sine to the 2 with sine to the 2 cancels. Sine to the 2 minus sine to the 2, these cancel each other. The other way that you can simplify the numerator is to say cosine to the 2 plus sine to the 2 is 1. Minus cosine to the 2 minus sine to the 2 is minus 1. They cancel each other. So these terms, this cancels with this cancels with this. What remains in numerator? 2 cosine sine, 2 cosine sine. In total we have 4 cosine sine. So we have, in numerator, we have 2 cosine theta sine theta and another 2 cosine theta sine theta. There is a good reason that I left it in this form. Otherwise you can write it 4 sine theta cosine theta or 4 cosine theta sine theta. But let's leave it in this form for now. And let's leave the denominator cosine to the 2 minus sine to the 2. Now for this we remember the identity. 2 sine theta cosine theta is sine of 2 theta. And 2 sine theta cosine theta is sine of 2 theta. So in total we have 2 sine of, so this is sine of 2 theta, this is also sine of 2 theta, so we have 2 sine of 2 theta over cosine of 2 theta. Sine over cosine is tangent, so this equals 2 tangent of 2 theta. We got to the other side of the relation. In this video, I try to show you not only how to prove identities, I try to show you the way that I am thinking about proving identities. The process of thinking, the process of using identities, the process of common denominator, why we do the common denominator at this step, why we use this particular rule at this step. I'll try to show you all the details. Now you should be more familiar with proving identities for trigonometric expressions using double-angle identities. If this video was helpful for you, please subscribe in my channel and see you in the next videos.